Hello, so today we'll be taking the sixth knowledge transfer session and we'll be covering regularization and optimization methods. And we'll start with regularization. So I think it's common knowledge that there's a problem in machine learning where we're trying to find an algorithm that performs not only well on our training data set, but also equally well on our test data set or unseen data. And so while developing these algorithms, there's this issue that we encounter that is called overfitting, where although the training accuracy is low or high and the loss is low, you can't say the same for the validation or test set, and the gap between the losses and the accuracy is high. So we would have covered this in previous sessions, but just to give a brush up over it, this is kind of the spectrum of model behavior. It ranges from underfitting to overfitting, and the balance between the two is a good fit or a robust model. So in underfitting, the model over generalizes and is not able to capture relevant patterns in the data set. And it's too simple of a model basically, and overfitting is the opposite, where the model is too complex and basically generalizes to or memorizes the training data set and is not able to generalize to unseen data. And this middle graph is kind of what we try to achieve when we build a model. And at the crux of this is something called the bias variance trade-off. So bias, you can think of bias being a high value signaling that the model is too simple, and variance having a high value signaling that the model is too complicated. So a high variance and a low bias is characteristic of overfitting, and a high bias and low variance is characteristic of underfitting. So when we try to find the balance between these, we achieve the optimal model complexity. So coming to regularization, it may be defined as a modification or change in our algorithm that helps us bridge this gap between the losses or accuracies of the train and test data set. And we're trying to reduce the error on the test data set without necessarily reducing the error on the trained data set. So it is a method to prevent overfitting. And this can be done in three broad ways. The first one being modifying the loss function, the second one being modifying the sampling method, and the third modifying the training algorithm. So we'll look at each one of these one by one, starting with modifying the loss function. So the first method within this is something called L1 regularization or lasso regression. And basically, the loss function you see over here, this first term is the original loss function, and the second term is the penalty term we add to it to get this new loss function. And here you can see this lambda term, which is a hyperparameter that helps us regulate the effect of this penalty term. And here we have to focus on the sum of absolute values of weights. So this is where we are trying to make the model not overfit to the data, and this is kind of what helps us do that. So what effect does this have on the model? So the primary consequence that we see when we apply L1 regularization is that it tends to drive some of the model coefficients to zero, and essentially it performs feature selection because certain features are excluded from contributing to the prediction of the output. So this naturally would be more beneficial when we have high dimensional data, when we want to reduce the number of features that we are working with, or if there's a lot of irrelevant or redundant features. So this is how it kind of helps us avoid overfitting. So just to build some intuition for why this makes sense, you can think of the sum of absolute values of weights as a constraint that kind of forms a diamond-shaped boundary, and then when you have to minimize the original loss function, the part where it would intersect this would first be at the corners, and the corners signify that some weights are going to zero. So that is how you can think of it as eliminating certain features and keeping certain other features. So to pick the best value of lambda, this is kind of a cheat sheet. So if you have a small value of lambda, it's kind of going towards overfitting because you're not really making that much of a modification to the loss function that you got for an overfitted model. So that would be low bias and high variance. And on the other hand, a large lambda would be more towards the underfitting, which would be high bias and low variance. So yeah, you're kind of finding the trade-off between fitting the data well, which is minimizing the original loss, and keeping the model simple, which is minimizing the penalty term. The second way that we can modify the loss function is L2 regularization, or also called ridge regression. So the penalty term is different here. We still have the lambda hyperparameter, but this time we have sum of squares of the absolute values of the weights. So instead of doing feature selection this time, we're kind of combating overfitting through a different lens. So here we don't make the coefficients exactly equal to 0, but we shrink them towards 0. So that's how it's different from L1 regularization. So in L1 regularization, we would apply it to, as I said, we would apply it to data that has a high dimensionality, or when we need to perform feature selection. But here, it's commonly applied to data sets where the features are very correlated or redundant. So we give a lesser weightage to each of the features so that the model doesn't start to overfit to a small subset of them and try to like kind of fit the noise within that feature. So all this that I described is basically the concept of sparsity, and that is the main difference between L1 and L2 regularization. So sparsity is when sparsity refers to the number of feature coefficients that we've reduced to 0. So as we looked at L1 regularization, as it completely turns the coefficients into 0, it contributes to sparsity, but L2 regularization doesn't. And that is the main difference between the two. Yeah, so we get a balanced contribution of all features rather than feature selection in L2 regularization. I'll pause here if anyone has any doubts. Okay, let's move on to the second method to combat overfitting, which is modifying sampling methods. So this is basically related to the data that we input into the model. The first one is data augmentation. So we do this to increase the size of the data that we feed into the model by enhancing it or augmenting it with certain transformations, such as cropping or dilating or adding noise or rotation and things like that. So we're trying to create more data so that we enable the model to learn a better representation of features. So this is kind of an example of the ways that we can augment data. So let's just pick like over here, edge enhanced data augmentation. So you can see the edges of the butterfly are more broadened and enhanced so that it lets the model capture this nuance of the data better if it didn't already capture it in the original input data that we fed it. The second way that we can modify the sampling method is something called k-fold cross-validation. So you would see that when we write code, a lot of the times we do a simple train test split where we just fix the validation data to be some 20%, for example, of the entire data set, and we don't really think too much of it. But there are certain cases where that 20% could just by some chance have certain patterns that aren't really reflected in the 80% of the data that we use for training, or there's just a mismatch and it doesn't let the model learn all the features and hence perform well on the validation set as well. So to combat this, we can apply this k-fold cross-validation where the test set essentially covers the entire data set with every iteration. So if I have 5 as my k, then that would be 5 iterations where the test set becomes a different 20% of the data each time. And the remaining 80% is used for training. So yeah, to do this, we would shuffle the data first. And then a a common value of k is somewhere between 5 and 10. And yeah, we keep one fold for testing and remaining folds for training. Yeah, and so what this does is it gives us a more reliable value of our losses, and we can take the mean or sum up the scores and take the mean to get a more well-rounded explanation of how our model is behaving. So it kind of lets us, if originally we thought that the model is not overfitting because of the certain distribution of our validation set, this kind of prevents that because we test it over the other subsets as well. And then the final way of regularization is the algorithm itself. And we look at two things here, the first one being dropout. So what happens in dropout is it's applied to neural networks, and what you do is you have a certain value of dropout that you decide for each layer, and that value is the percentage of neurons or nodes in that layer that are excluded from the training process. So you just temporarily ignore those neurons while you're training and all the weights that come into it and come out of it. So what this does is it helps the model kind of basically the neurons are not dependent on each other to form the output, and they independently learn important features. So it helps the model focus on the features that are truly important and not kind of model noise as the capacity increases when you don't have dropout. So this is a visual representation of what dropout looks like. You can see these in the second or hidden layer, these two neurons, so say the dropout percentage is 50%. So two of these neurons out of four have just been ignored, and all the connections that are going into it and coming out of it have also not been considered during training. And dropout is only applied during training. It's not applied when you're at inference. Yeah, so like I said, it just ensures that the neural network learns a more robust set of features and performs equally well with random subsets of the nodes selected because they are not dependent on each other now. So yeah, you get a more generalized model and a more robust model, and hence this reduces overfitting. And a good value of dropout is seen to be 0.25 to 0.4. And then the second method is drop connect, which is similar to what dropout does, but it's implemented a little bit differently. So in dropout, we ignore the neurons or nodes, but in drop connect, we set weights to 0. So it's a different way of forming a sub-circuit within the network. And because we have so many weights going into neurons and coming out from them, naturally it makes sense that it's more computationally expensive to find a good network after applying drop connect because there are so many weights that you could possibly turn to 0. And figuring that out is computationally expensive, and although it does give us finer control than dropout, and it's not really seen to give better performance unless I'll take that out after this, unless we have a really small network. So yeah, that's why it's kind of less commonly used and more so unsupported in standard libraries.
So hi everybody. So I'm going to be taking optimizers. Yeah. So first let's start with what is an optimizer. So we know that the whole point of like training models and making models learn is to reduce their error. Like you have a function which basically measures how far the model's predictions are from the actual values. And you want to minimize that function so that the predictions match the actual values as much as possible. So you want to tweak the parameters of the model to make it match the actual values as close as possible. So optimizers are just algorithms or methods that help you do this, like help you minimize the error function and also do this in an efficient and resourceful manner. And yeah, so these are just functions and they're dependent on the weights and biases or the parameters of the model. Um, so yeah, so like we've covered what optimizers are essentially. Then there's also an important term that we always use called loss function. So what exactly is a loss function? Okay, so a loss function is just something that measures the deviation of the predicted value from the true value. It can be any function. And normally for linear regression, where you want the values of the model to exactly match the values of the actual values, you use mean squared error. It is just like a square difference between the values. And if you want to do classification, you'll use like binary cross entropy loss or something that measures how confident the model is at choosing the right answer. So this is just going to measure how good the model is, or like how the loss function measures how bad the model is, and you want to minimize this function. And so how is this loss function and optimizers related? So yeah. So the main goal of deep learning is to reduce the loss or error in the model. So how this is done is like an optimizer acts on the loss function and updates the parameters so that you minimize the loss function as much as possible. Like this is all stuff that we mostly know. It's very familiar. And yeah, you want to reach the global minima or the absolute lowest point of the loss function. And how do we determine it is done by optimizers. And yeah, so for mean squared error, the plot of a loss function is essentially going to be like a paraboloid. It's just like squared function of the weights and biases. So it's going to look like this, and there's going to be a minima. And the optimizer's job is to find ideal values of these parameters, like theta naught and theta one, like which can be multiple weights and biases, so that you actually reach this minima. Okay. So, what are the types of optimizers or algorithms that you can use to do this? There's multiple ones. The first one is like gradient types of gradient descent, which can be gradient descent, stochastic gradient descent, or mini batch gradient descent. Then you have methods that incorporate momentum into this gradient descent. Like we'll get into that later. And there's methods that also like tweak the learning rate. We'll also discuss what a learning rate is later. And there's also methods that combine both of these. Like you adapt the learning rate dynamically, and you also use like momentum. And there's also something called look ahead, which is like completely different. And we'll be mostly covering momentum and like the types of gradient descent, momentum, and adaptive learning rate methods now. And yeah, so gradient descent is something that we all know. It's like the most basic optimization algorithm, and it's used heavily in linear regression and classification. So gradient descent is just moving in the direction, like in the reverse direction of the steepest like slope. So if you have uh, okay, no. If you have like a loss function and like you have a point where the slope is really steep, you're going to make a larger step in the reverse direction. So, and like the thing is, if the slope is positive, like, yeah, I don't know where I put the diagram where it was more clear, but like if the slope is positive, you essentially want to move backward because the minima is going to be backward from that point. And if the slope is negative, uh, you want to move forward. So like I'll tell you exactly what the mathematical equation is. So that's what gradient descent is. And now that we know like in which direction to move, gradient determines the direction to move, and which is basically a steepest slope of the loss function. How big of a step are you going to make? So, like the size of the steps that you make in the direction of the steepest slope is determined by the learning rate. So you scale the gradient by this learning rate and make a step in that direction. And this is also, it's a hyperparameter, meaning it's like specified by the user. And in some cases, the size of these steps is constant throughout the optimization process. And in some cases, it's dynamic and it changes with the gradient to make more stable convergence. That's what adaptive gradient methods are for. And we'll be discussing that later. And the thing is, you need to ensure that the learning rate is an optimal value. It can't be too high and too low. So if the learning rate is too low, you're going to make really small steps. So the convergence is going to be really slow. if it's too high, you're going to make steps that are too big. So like, yeah, here, if you start at this point, the gradient is going to be like positive. So you want to make a step backward. So you essentially want to make a small step backward, or at least like something that takes you to this point. But if the learning rate is too high, you're going to make a really huge step and cross the minima altogether. And just like cause it, the update is going to be too drastic. So this is also not going to let you converge. So you want to take a value that's just right. So it's not too slow that it's not converging at all, and it shouldn't be too high that it's going to oscillate too much. And yeah, so if we look at it in a graphical manner, if you have a very high learning rate, it's not going to converge at all. If you have a low learning rate, it's going to converge really slowly. Like this is a loss versus epoch curve. And yeah, and if you have a high learning rate, like it's gonna converge, but like not as well. It's gonna like not reach the minima. So, but if you have a good learning rate, that's a mix of both. It's gonna converge quickly and also like reach the minima properly. And yeah, an epoch is just like a number of iterations in which it has gone through the entire data set. Like one epoch is the model going through the entire data set of points. Yeah, okay. And yeah, this is the equation for updating parameters. It's like you take some parameter and the new value is going to be you subtract like the value of the gradient but scaled by the learning rate. So you're going to move in the reverse direction of the steep gradient. And yeah. And now let's get into the types of gradient descent. So we have stochastic gradient descent, batch gradient descent, and mini batch gradient descent. Okay, so stochastic gradient descent is the one that we're going to discuss first. So the word stochastic means a randomly defined process. And so what you do in stochastic gradient descent is you take one point from the data set, you compute the gradient of the loss function for just that point. You get the loss with respect to that point, you compute the gradient, and then you update it based on this gradient. And yeah, so but then you're essentially just asking one data point where to go. Whereas there's a lot of data points in the set, and you should be asking everything to make the best step towards the minima. But you only ask one point because this is more computationally efficient. Like if you were to compute the gradients with respect to every single point, take the average, then make that step, it's gonna take so much computational power and it's gonna be really slow. So for faster convergence to the minima, you use just one point and you randomly pick it up. And the thing is, this is going to be very noisy. Like it's not going to be the right direction. So if you just take one point, it's going to be in a different direction than the best path towards the minima. But the thing is, since you're taking all the points like one by one, the noise of one is going to balance out the other, and you'll finally end up reaching the minima, even though it will be not the like most direct path. And the next one is batch gradient descent. And this one is like you take the entire batch of data points. So every single point you take the gradient with respect to that, and then you make the step based on the average of all these gradients, the mean gradient. And yeah, so this has a lot of computation and it's not really feasible. But here it's not going to be noisy at all. It's going to be like a perfect calculated path towards the minima. It's going to be shortest path towards the minima. And yeah. And so then the next one is it's going to be like the best of both worlds. It's not going to be too noisy and it's not going to be too computationally expensive. That's mini batch gradient descent. So it's like a combination of batch GD and stochastic GD. And what you do is instead of just taking one point to calculate the gradient, like stochastic gradient descent, you take a mini batch. So you have a set of data points and you take a random subset, a smaller subset from this data points. Then you calculate the average gradient from that subset of data points. Then you make the update. So what you're doing here is you're taking information from more data points to make the step than in SGD. So it's going to be less noisy. And at the same time, you're not calculating it for all the points, like you will have millions of data points. So it'll be less computationally expensive. So yeah, so this is going to be better than either of those two methods, and it's the one that's used most commonly. So this is like a visual of what all those three looks like compared. So batch gradient descent is going to be like a perfect line towards the minima. Stochastic gradient descent is going to be like very noisy. It's going to like not be, it's going to be very zigzaggy. And mini batch gradient descent is less zigzaggy than this, but it's not as perfect as this one. So yeah. And yeah, so the accuracy for batch GD is going to be the highest of each step, but it's going to be a lot more time consuming. And for stochastic GD, accuracy is going to be the lowest, but it's taking the least time. And mini batch has moderate values for both. So this is the one we choose a lot. And yeah, so now we've talked about reaching the minima, but normally in loss functions, it's not going to be like a perfect paraboloid with just one minima. It's going to have multiple minimas. So you want the optimizer to find the global minima, which is the smallest minima. And will it be able to find the global minima if like you just use regular gradient descent? And like the answer for that is no. Like you're not going to be able to find the global minima. It's just going to settle in the first minima that it finds. To fix this, we use something called momentum. So SGD with momentum is an algorithm where you add a certain momentum term to the like gradient descent process. So it's not just one step, but like you're gonna have some momentum to that step that's gonna allow it to pass over those local minimas. Like the minimas that are not that deep, it's not gonna stay there. It's not gonna settle there, but it'll pass over and it'll only settle when the minima is like deep enough and it's a global. So, how you do this is instead of updating the values with just the current gradient, like this is a parameter, theta t plus 1 is going to be equal to theta t minus learning rate into like just the gradient of at that point normally. But here, instead of using the gradient, you use an exponential moving average of all the gradients to this point. So let's get into what exponential moving average exactly is. So this formula over here like explains that well. So this beta is just a hyperparameter that we set, and it's called the momentum coefficient. So how you do it is like this point, like the exponential moving average is going to be beta into the like previous velocity term plus 1 minus beta into the current gradient. So what this is this VT is going to contain information about all the past gradients, since this is also computed in a similar way, except that it's going to be beta into VT minus 1 plus 1 minus beta into the gradient at t. So like this VT is going to contain information about all the past gradients. So you're incorporating beta times the past information and 1 minus beta times the newest gradient. So you're incorporating information from where you were before. So that is gonna help the model make a more informed decision on the next step. Instead of just the current gradient, it's gonna remember what direction it was moving in essentially till now, and it's gonna make a better, less noisy step in the next one. And if you actually look at this, the last kth gradient, so you have a bunch of gradients when you start to a point, right? So the last kth gradient at the last kth time step will get a weight of beta power k into 1 minus beta. Like if you actually look into this equation, like if you keep substituting like t minus 1, t minus 2 into this vt, you will understand that it will be beta power k into 1 minus beta. So what this does is like as k gets higher or as this gradient gets older, it's going to get a less weight. And the more recent gradients get more weight. So this is very good and dynamic where like really irrelevant gradients and irrelevant steps from the past, you forget them. And the recent steps you remember so that you can make a more informed decision on the next step. Um, yeah, and so that's all mostly. All these points are pretty simple. Yeah, but so the point of this is you don't want to settle at the local minima, but since there's some momentum from your past steps, you want to skip over the local minima and reach the global minima, where even if you have momentum, it's deep enough that you settle there. Yeah, but still, there's also a good chance that the model might overshoot the global minima itself, in case it's like just not that deep. So to counter this, to make settling more stable, you use adaptive learning rates. So one of the most popular optimizers which uses an adaptive learning rate is RMS Pro. So what adaptive learning rates does is you take the learning rate and you scale it based on the gradients. Mm, So the equation for this is theta t plus 1 equals theta t minus alpha by root over et plus 1. And this et plus 1 is an exponential moving average, but instead of just the gradients, you square the gradients. Like we covered what an exponential moving average is like before. So you take the squared gradients, you take the exponential average of that, so that the older gradient square get lower weights and the recent ones get higher weights. And then you basically scale it down by that factor and then you update the gradients. Like you're just changing the learning rate here. So even here, beta decides how much of the old data should be remembered. If it's high, it's going to remember the older steps more. And so this epsilon might be confusing, but that's just to prevent like dividing by zero error in case the gradient gets really small during the final steps. So you just have a constant here. And yeah, and this one does not have any momentum term, it's just normal gradient updation. There we saw that we updated it on the exponential moving average. Here we're just updating it on the gradients. And yeah, and this learning rate is scaled by the running average of the square gradients. So what happens is when your squared gradients are really high, so if you're going through a really steep slope, the gradients are going to continue to be high and this exponential moving average will be high. So the learning rate will be smaller. So if you have a really steep slope, you want to move slower so that you reach the minima more stably. Like if the gradients are high and you don't use any adaptation for the learning rate, you're just going to make a really large step and you might bypass the minima. So to prevent that, you're scaling the learning rate and making it smaller when the slope is really steep. And when the slope's not steep, it's like a flatter region, you want the learning rate to be higher so that you move faster and reach minima faster. So yeah, a steep slope will lead to smaller steps, which will make it more stable. And also the model is faster when it approaches local minimas, which are flat. And I said that if it's flat, it's going to move fast because the learning rate will be higher and it will not get stuck in local minima. It will only stabilize when the minima is properly deep and it's a global minima. And now Adam is the final one, which is the best of both worlds. It combines both SGD with momentum and it combines with RMS Pro. So you get an adaptive learning rate, which will help you settle at minima properly. And you also get momentum, which will help you bypass local minima and reach the global minima. So yeah, exactly. So what you do here is you update it with a scaled learning rate. And this VT is going to be the moving average, exponential moving average of your squared gradients, like we saw in RMS Pro. And this MT term is going to be the exponential moving average of your gradients, which we saw in SGD with momentum. And so you're just combining that in the updation. And one important thing in Adam is you also use something called bias correction. So what you do is you scale this MT and VT, which are termed the first moment and the second moment, by 1 minus beta 1 power t. This beta 1 corresponds to the first moment, beta 2 corresponds to the second moment. And why you do this scaling? It's not scaling down actually, it's going to be scaling it up because beta 1 minus beta is going to be less than 1. So why you do this is when the model starts converging, MT and VT are going to be initialized to 0. And so basically the all the history about gradients it has is 0. So all the gradients that it calculates or the averages that it calculates after are going to be really small because you're getting a beta times 0 there. So these small values are going to be too small. They're not going to give you enough information about the actual gradient. So what you do is you scale it up to make it closer to the actual gradient at that point. And as the steps get more and the model kind of learns and starts stabilizing, the t like basically t will get larger. So beta per t will get like really small, close to 0. So it'll just be MT by 1. So it'll just be MT and VT. So there won't be any problem. So it's just to help it because it'll have some starting trouble, just to help it stabilize in the beginning. And so yeah, I think we've covered everything. And ADAM stands for adaptive moments. And these two averages are termed as like the first moment and the second moment. So now that we've talked about all the optimizers, I also wanted to mention that there's different types of minima in the loss function landscape. So they might be like the same depth, but they'll be different in structure. So it'll be, if you look at this one is a flat minima, and this one is a minimum, and this one is a sharp minimum. So the thing is, you want the model to find flat minimum because flat minima are better at generalizing. So the thing is, like you reach like parameters that get you to this minimum point, and if you make even a small tweak in these parameters, like the loss is not going to change much. If you make a small tweak, it's going to still stay low. Like the loss value is still going to be low. But with sharp minima, even if you make one tiny step in like in like a small direction, it's going to be the loss is going to be really high. So it's basically overfit to these parameters. So it's going to be bad at generalization. So you want the model to find flat min. And this is why SGD with momentum generalizes better than Adam in a lot of cases. Because Adam is good at settling at like deep, sharp minima, while SGD cannot settle in a sharp minimum. It'll always bypass it and find a flat min. So yeah, that's why it's there. And now we'll get on to like a simple code implementation. Are there any doubts? Okay, I'll continue. Uh, yeah, 1 second. Okay, so yeah, I'm just gonna show you how to do like mini batch gradient descent with PyTorch. So you're just importing all the torch libraries to make like a simple neural network. And there's an important module called data loader. So what data loader does is it helps you make mini batches from the data. And I'm just creating a like simple data set, X-train and Y-train. And then, yeah, it's just going to be a random set of 1,000 samples and 10 features. And it's going to be classification data set. So I'm just getting random zeros and ones for each one of these. And then defining like a simple neural network. And it's going to have 10 input nodes for the 10 features. And it's going to have 32 nodes in the single hidden layer. And then it's going to have one output node. And yeah, it's just a forward pass with a relu as the activation function and sigmoid to get the probabilities. And then I'm just defining like a simple get optimizer function so I can like change the optimizer easily to show you guys. And yeah, so we have SGD. With Torch, you just have built-in modules for each of these optimizers. So for simple SGD, you just use torch.optim.sgd and you don't give it like any momentum term. Like the default momentum is going to be 0. So it's just going to implement vanilla SGD. And if you want SGD with momentum, like you specify a momentum term and it's mostly 0.9. And for RMS prop also, I've torch.optim.rmsprop. And yeah, here the alpha is the term, like it's the coefficient, momentum coefficient for those squared gradients. And yeah, Adam, it will take default values for like the two momentum coefficients. And yeah, so the model is like the neural network we built. And I'm taking BC loss because it's classification. And like this is the optimizer. So like to start with, we can just use like simple SGD. And here is like the part where we create mini batches. So you create that into like a tensor dataset, the regular NumPy dataset into a tensor dataset. Then like I'm loading the data and making it into mini batches. So here's where data loader comes in. So you just put in the data set, specify the batch size. So it's going to be 32 data points per batch and shuffling is enabled. Then this is just to hold like the losses per mini batch so we can like see. And we're going to do 10 run throughs of the whole data set. And so yeah, so this code is for mini batch gradient descent. So you like do a for loop where you cover like each mini batch one by one. So mini batch X and Y in the data loader, like train loader list. What you do is you just get the model outputs for that mini batch, compute the loss for that mini batch. Then you make the step based on the gradients for that single mini batch. So for that, it's just like you set the gradient memory to 0. Then you do backprop. and like make a step using the gradients of this mini batch. Then yeah, so I'm just adding the losses so that we can plot it out later. And this is just plotting the loss per batch. So yeah, we're using just simple like gradient descent with a batch size of 32 mini batch. So let's see how that goes. So yeah, it's like pretty noisy, but it's like okay. Like if you compare, like I'll show you how just a single SGD works, and that'll be really noisy. So we've looked at that. So to do like SGD with just one data point at a time, you just set this batch size to 1. So we'll work on that. So look at this, it's like extremely noisy as compared to what we saw before. So like mini batch gradient descent is like a lot better. And now we'll try out like momentum. So I'm going to just set it to mini batch gradient descent because we know that's good. And now we'll focus on making that even better. So for the optimizer, we'll put SGD momentum. Then we'll try that out. So yeah, this is like even less noisy than the mini batch gradient descent without momentum. And then we'll try RMS drop. Now that's not going to have any momentum. It's just going to be adaptive. Just going to be adaptive learning rate. And yeah, so like you have even better convergence here. Then we'll finally try Atom. So yeah, it's reaching like the least loss even better with Atom. So yeah, that's the code implementation. And I think we can come to an end unless anybody has any doubts.